Dear participants, we have our speaker, Dr. Professor Sabu Thomas with us. We are indeed extremely pleased. In fact, we are privileged to have a speaker as such amongst us. It will be my pleasure to read out his biodata. I mean, I need an entire class to do that, but I will try to just point out the highlights of Professor Sabu Thomas's distinguished career. So Professor Thomas did his BSc, in majoring in chemistry from University of Kerala, and his BTech in Polymer Science and Rubber Technology from University of Cochin, his PhD from IIT Kharagpur, Polymer Blends and Thermoplastic Elastomers, postdoctoral fellow in Quebec, that is Macromol Science Engineering Research Center in Canada, and 2 stints of postdoctoral fellows at Catholic University Leuven, Belgium. So this is, and then of course, his I would like to read out his major achievements. Currently, is the Vice-Chancellor of the Mahatma Gandhi University, Kottayam, and he is also a fellow of the Royal Society of Chemistry, London. He was a Fulbright fellow in the US. He is a professor at University of Lorraine, Nancy, France. He has an H index, hold your breath, of 112. 112 is his H index. His total number of publications cross 1,000. His total number of citations is 60,000 plus, 60,742, Google Scholar. 15 patents, 4 granted, filed 11. Number of edited books, 158. Number of PhD thesis supervised, 115. Nationally about 100, internationally about 16. He has carried out so far 40 projects, totaling to some 23 crore rupees. He is cited in the list of the most productive researchers in India in 5th position. He has also won the Best Faculty Award in 2018. He's a chief editor of an international journal called Nanostructures and Nano Objects, Elsevier Journal. He was voted as the Trila Academician of the Year in 2018. He's a foreign fellow of the European Academy of Sciences, fellow of International Association of Advanced Materials. He's cited among 2% scientists in India by Stanford professors. And from the Kerala government, he has also won the Kairali Lifetime Research Award. The very fact that he is the Vice-Chancellor of the most prestigious Mahatma Gandhi University itself speaks volume of the zenith or the pinnacle that he has reached. Of course, his research areas are quite a few: nanomaterials, polymer blends, polymer composites, nanocomposites, and so on and so forth. And he's also had more than 50 instances of visiting professor. He has worked as a visiting professor for various durations in at least 50 different times. So a couple of them, in 2002, he was a visiting professor of CNRS Laboratoire de Recherche sur les Tiers, Paris, France. He was also in Belgium, in Centre de Recherche sur la Matière Divisée, Orléans, Cedex de France. And then, of course, in so many research centers and universities in Beijing, in Germany, in Slovenia, in Spain, in Korea, in Poland, Malaysia, Austria, China, Guyana, Hong Kong, Brazil, you name it, he has been there. And not been there to present paper, he's been there on a visiting professor assignment. So all right, so he has worked in the industry, in the industrial also. He has worked as a rubber production officer in Bata, India. He's also worked as a technical officer in Bayer India Limited from the industrial point of view. He has, as I said, he's a member of different boards, chairman, board of studies, dean of faculty, and so on, and vice-chancellor currently of the Mahatma Gandhi University, and his invited lectureship abroad. The professorship is different, where he teaches. With invited lecture, again, runs into dozens of instances. Sir, I cannot say anything more. That we are really, really pleased, and it's a privilege for us to have a distinguished speaker like this. And we are very happy that you have accepted to come on board to this thing. It's such a wonderful thing that this online FDPs have allowed us to get speakers like you. And sharing of knowledge is at an all-time high, thanks to this online initiatives. Sir, I let's say it's about 10, 925 or 1927 now, you can speak up to 10:15, and between 10:15 to 10:30, you can take some questions. You had told us that you want to leave at 10:30. I mean, if you can, I mean, if you want to extend it, we are free. We are free up to 11 o'clock. So, but if you want to quit 10:30, maybe the last 15 minutes, you have to take some questions, sir. Over to you, sir. We are all very keen to listen to you. Sir, thank you.
Thank you so much for your kind words of introduction. I'm extremely sorry for the trouble happened in the beginning because of some network issues and some problem with my sound system. And many, many thanks for the kind words of introduction, kind invitation for this wonderful FDP program. I will directly go into my topic. I was asked to present something on green materials. Can you all hear me? Can you hear me?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
I
Yes,
am
sir.
asked to present something on green materials. So I thought of the best could be some of our recent work on nano cellulose, nano chitin, and nano starch. So I will focus more on nano cellulose. So the title is New Opportunities in Sustainable Green Nanomaterials. Why I use sustainable is because you will see that these materials could be extracted from agricultural waste, renewable. That's why I gave the name sustainable. Those who are really interested to look at my work, you can read sabuthomas.com and iiucnnemgu.ac.in. I was with Mahatma Gandhi University for the last 35 years. After my PhD from the Indian Institute of Technology, I had a small stint at the Bayer India Limited. Then I joined here and made a very big group in Mahatma Gandhi University. My focus is more on sustainable materials. I'm going to show me the first slide. I wanted to show you a beautiful statistics. 1.6 billion tons of agro waste is being accumulated every year around the globe. This is from American Chemical Society. The slides are moving? Professor Panish, the slides are moving?
Yes, sir. Yes,
Okay.
sir.
Yes, sir.
1.6
Voice is
billion
little low,
tons
sir.
of agro waste. Can you hear me well?
I suggest all the participants to increase their volume when you'll be able to.
Volume because I have moved into another computer.
Okay, sir. No problem. Yes, sir.
My wife and my system, there was some trouble.
I know. And if we increase our volume, we are able to hear you fine, sir.
Yes. Please
Thank you,
increase
sir.
the volume. This system has some trouble with the volume. That could be the reason.
Yes,
so
sir.
American Chemical Society says 1.6 billion tons of agro waste is being accumulated all over the world. And these agro waste are being these materials for making advanced functional materials. I have a big group in this area. Go to agricultural land, collect the waste, and transform into advanced functional materials. I will go to the next slide. You see, we have lots of fish industry in India. And from the fish waste, especially the shell of prawn and crab, we make use of them to make nanochitin. Let me go to the next slide. Look at the agro waste. We have a variety of agro waste. Bagasse, sugarcane bagasse, after extraction of, the juice from yes, you get this bagasse and this is a waste. Wheat bran and rice bran, corn cob, wood flour, jute, coir, variety of agricultural waste. And I wanted to show you the commercial production of this material worldwide. If you look at the commercial production of this material worldwide, you will see that wood flour is number one, followed by bamboo, cotton, kenaf, flax, hemp, got lots of natural fibers. Kerala is gifted with a lot of coir. We have many, many industries based on coir. Kerala is also gifted with a lot of pineapple leaf, banana. But if you look at, except coir, many fibers are not being effectively utilized for value addition. Let me go to the next slide. Look at the plant fibers. Plant fibers are very interesting material. Environmentally, they are very friendly. I would use the word benign. Cost effective because they are not very expensive like glass fibers or synthetic fibers. Abundant. They are not abrasive to machineries. I mean, you are all engineers partly. When you mix glass fibers, a lot of wear and tear on the machineries. But natural fibers, they don't give much of trouble. Excellent acoustic properties, thermal insulation properties. So I can list large number of advantages. Let me show you the different types of natural fibers. Natural fibers extracted from the stem, we call this bast. Good example is jute. We have a lot of jute in the country. Fibers extract from the leaf of the plant. The best example is pineapple leaf. We are now starting a company on the campus to make nanocellulose from pineapple leaf. Seed, best example is coconut. We extract the fiber from the seed. Grass, so we have a variety of ways classify them. I have some pictures of banana, oil palm, pineapple, coir. We have lots of coir industries in Kerala, but not many pineapple industries, pineapple leaf reprocessing only, not many. Look at the price. Let me show you the price of this material. Taking cotton as an index of 100, you will find that they are relatively cheap. You can look at the cost of coir, wood, or straw. Now, let me show you, you're all engineers, you will be interested in the technical properties, the mechanical properties of this material. They all give pretty good mechanics, tensile properties, Young's modulus, elongation at break. Interestingly, look at the density of this material. They are all pretty light compared to glass. Therefore, the specific properties are superior to glass. They can compete with glass in terms of specific properties, property divided by density. Let me show you the next slide. If there are some chemists in the audience, you will find that lignocellulosic materials are fascinating molecules. If you look at the composition of lignocellulosic material, plant fibers, basically cellulose. Look at the structure of cellulose. And you have wonderful hydroxyl groups. You can do a lot of chemistry on the surface. The second important component is lignin. Lignin is a very complex hydrocarbon. You can see the structure of lignin. And the next one is hemicellulose. See the structure of hemicellulose. What we are trying to do is, we are trying to separate out the cellulose and use them for a variety of applications. Now let me show you the hierarchical structure of plant fiber. This is something very interesting. If you look at the hierarchical structure of plant fibers, look at the plant cell. This is quite big. Macro. And you can have a fiber. Look at this. This is again a macroscopic structure. But inside this fiber, you have lots of microfibers embedded. You can separate them, so you get microfibers. And inside the microfiber, you see lots of nanostructures. You see? So you can work in three different landscapes, three different hierarchical landscapes. The macro landscape, the micro landscape, and the nano landscape. Right now, my research group focuses more on the nano scale. A lot of work on micro length scale. So we have lots of extraction protocols to extract the nanocellulose. Now, let me show you another important slide. Why nanocellulose is important? Friends, I would say the most important nanomaterial so far mankind has used. I would say nanocellulose is number one. It can beat many of the synthetic analogs, CNT or graphene or such materials. You know why? They have excellent mechanics, highly crystalline, low density, high specific properties, high water holding capacity. I mean, you can do a lot of chemistry on the surface. Let me show you. I would say nanocellulose is the most important strategic platform for sustainable development. Carbon nanotube is not good because I just got a lot of toxicity. My group is active also in carbon nanotube. Graphene, much better than carbon nanotube, but not as good as nanocellulose. Let me now show you the electron microscopic picture of nanocellulose. Look at this is the electron microscopic picture. If you examine nanocellulose under electron microscope, high resolution electron microscope, you will see like this. You have a continuous wave-like structure. And the width of these, the diameter of this cellulose is something like 20-25 nanometers. And they're pretty long. It could be even micrometer long. And if you make nanocellulose and if you put inside a transparent glass tumbler, you see this is nanocellulose gel, transparent gel. How do you make them? The technology has been matured. Acid hydrolysis, steam explosion process, super grinding process invented by my Japanese friends, cryo crushing process, high pressure homogenization process, high intensity ultrasonication. So these technologies have been matured now. So laboratories all over the world use different techniques to manufacture nanocellulose. Let me show you high pressure homogenization. What do they do? If you look at high pressure homogenization, the process includes passing the cellulose slurry at high pressure into a vessel through very small nozzle. And you subject this nanocellulose to very high shear forces. And because of high shear forces, you can fibrillate, you can get nanoscale. Look at the super grinding process invented by Japanese colleagues, Professor Abe, Professor Iwamoto. You can see this biomacromolecules paper. The next method is high intensity ultrasonication process. There also you apply high shear force and then you come to nanoscale. Let me show you steam explosion process. If you look at steam explosion process, what is being done is you subject this agricultural waste, the lignocellulosic material, very high temperature, 150 degrees Celsius, and a pressure of 137 Pascal. You know what happens? Once you load them into the autoclave and you increase the pressure and temperature, after a while, maybe after 10 minutes, you release the pressure suddenly, then you have an explosion. And because the explosion, the macrocellulose is opened up and you get beautiful nanocellulose. We have this technology in our laboratory. We make use of steam explosion process. Let me show you my next slide. The totality of the event, what we do in my laboratory, my PhD students go to the plantation, collect all this waste, clean them, dry them, and then we first subject them to alkali treatment. When you do an alkali treatment, you can remove lignin hemicellulose. And then we get a slurry We go for an acid hydrolysis, treat the stuff with either strong acid or a light acid. When you treat with a strong or light acid, what happens is you can remove the amorphous part, lignin hemicellulose. If you use a strong acid, you completely remove all the amorphous part and you get crystalline cellulose, completely crystalline cellulose, we call nanocrystals. And then you go for a homogenization process, you see a milk-like material. This is nothing but nanocellulose suspension. And if you take a drop of this and put under electron microscope grid and evaporate to the water, you know what you get? You get a beautiful web of nanostructures. So this is the totality of the events, what we do in a laboratory. You can make either long nanocellulose. You can also make short nanocrystals. The difference is when you have a long nanocellulose, you have both amorphous and crystalline segments coexist. If you look at nanocrystal, you don't see any amorphous part because you have used a strong acid. You kill all the amorphous part. So dear friends, you have two options. Either you can make long nanocellulose or you can make short nanocrystals. You have two possibilities. If you use strong acid, you get short nanocrystals. Let me show you let me show you it's not opened up. Let me show you my the work of Mohammedan group from Europe. Mohammedan group did something very interesting. Just a minute. They made use of, can you see my slide? Dear friends, can you see my slide?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Mohammedan group, they made use of sulfuric acid. And they could make short nanocrystals. You see, look at Shanyod. They could make short nanocrystals. Beautiful short nanocrystals they could make. You see the nanocrystals. They started from wood flower. I will show you my setup in MGU campus. You see, we go for, in MGU campus, we have a steam explosion unit. Look at our explosion unit. Look at this. My PhD students collect the agro waste, put into the steam explosion unit. We go for a bleaching, acid hydrolysis, mechanical agitation. Finally we get nanofibers. This is a setup we have. If any of my dear friends want to utilize this technique, please visit my laboratory. And let me show you the dynamics of the enrichment process. You see, when you collect raw fiber from the plantation, the cellulose content is 64%. Hemicellulose is 18.6 and lignin is 4.9. But when you do this chemical treatment by steam explosion, bleaching, the amount of cellulose goes up. You get 95.86%. And you remove hemicellulose and lignin by chemical hydrolysis. And you get really very high quantity of nanocellulose. Let me show you some nice pictures of nanocellulose extracted my former coworker. He's now in the US doing a postdoc and he's staying back in the US. You see, nanocellulose we have made from banana stem. They're all nanocrystals, short nanocrystals by atomic force microscopy. Let me show you some work we have done in cooperation with Sweden. We had a long Swedish cooperation. Probably you know that Sweden has a lot of forest. So they are very active in wood flower. So one of my PhD students went to Sweden. Vice-Chancellor is right now an assistant professor in Russia. He made nanocellulose. It's an atomic force microscopy picture for wood flower. Let me show you another work we have done with Brazil, with the Sao Paulo University. We have extracted nanocellulose from pineapple leaf fiber. This is a FESEM picture. So dear friends, my laboratory is able to make nanocellulose from any agro waste. We have the capability to do that. And we have done lots of work in this area. Now let me show you another important slide. This slide is very important for chemists. You see, nanocellulose has beautiful hydroxy groups. If you're a chemist, you can do several reactions from the surface because these reactions are very important to make a strong interface. You can do tempo oxidation process. The OH could be converted into COH. You can do esterification reaction. You can do polymer grafting. You can put fluorescent labels on the surface of nanocellulose. You can do wonderful fluorescent spectroscopy work. You can do cellulation reaction. Recently, I signed an MOU with Apollo Tires to make use of nanocellulose for tire. So where we are going to do cellulation reaction, we can introduce silane functionality on the surface, so to make it less hydrophilic. You can do cationation reaction. So dear friends, lots of chemistries could be done on the surface of nanocellulose. It's not complicated at all. Now, let me show you what are the important applications of this material. My group made excellent products. One of the important applications of this material is water purification. Probably you all know that the amount of drinking water is being depleted. And UN says within 10, 15 years, we'll have a lot of water scarcity in this country. We have a lot of water scarcity in this country. So we have a strong interest on water purification. I will show you what we do in water purification. Look at this slide. We have a tri-layer configuration. See, the bottommost layer is made of non-woven microfiber support. It could be polyethylene oxide, it could be polyacrylonitrile, or it could be polyether sulfone. This is the non-woven microfiber support. This we buy. Over which you have the electrospun nanofiber support, which is mostly PVDF. On the top of this, you know what we did? We have given a coating of nanocellulose. This is a hydrophilic coating. You know, nanocellulose is extremely hydrophilic because of hydroxy groups. So this is the configuration of our filter, water filtration unit. They wonder. My research group tried to remove crystal violet dye. Probably you know that in the textile industry, you will find lots of dyes to give attractive colors. But dear friends, after dyeing, you know, they dump everything into river water. And our river water is getting polluted increasingly. Look at this. The crystal violet dye coming from the factory, polluting the river. So we try to remove crystal violet dye. I will show you a slide, but we did some chemistry in order to make the filtration process very efficient, removal process very efficient. We did some chemistry on the surface. This is cellulose, nanocellulose. My PhD student made nanocellulose, and we did a green chemistry. We reacted with the meltrum acid. Look at this. particles. Very simple reaction. And we introduced CO minus group on the surface of nanocellulose. Very simple chemistry you can do in a BSc laboratory. And then you will see, you might ask, why did we do this chemistry? If we do this chemistry, look at this protocol. So you have nanocellulose with the CO minus group. This is the dye being used in the industry. And this dye can have electrostatic interaction. So all these dyes could be captured by nanocellulose by this interaction. So if you don't do this chemistry, you cannot have this sort of interaction. And you will find that, you see, our filter is able to remove all these crystal violet dyes. And you can see the efficiency of separation. This is the commercial filter that you get in the market for dye removal. Look at our dye, our filter. Our filter is much more efficient. The top one is chemically modified nanocellulose. This is unmodified nanocellulose. Dear friends, I'm going to show you another important work. Again, water purification. Probably you all know that water has a lot of suspended particles. It could be iron oxide, it could be other suspended particles. We try to remove this using the same protocol. So we have used this filter, and the diameter of this filter, the whole diameter is the range of 8 nanometer or 8 to 9 nanometer. And when you try to separate out these suspended particles, you see, this is the filter after the filtration process. All the suspended particles were retained at the top of the filter. They're all iron oxide. See the bottom part of the filter, very clean. And we can recover all these nanoparticles and we can get pure water. Look at this, the impure water and pure water after filtration. So we are able to utilize these filter for removal of suspended particles. Those who are really interested can look at our ACS publication sometime back. Let me show you another important work from Finnish group. The Finnish group in Finland is very active using nanocellulose for cleaning seawater. Probably every day we read in the newspaper that the seawater is increasingly getting polluted due to the leakage of oil from the ship. Sometimes ship is sunk. So nowadays seawater is increasingly polluted by oil contamination. So our Finnish friends, you know what they did? They did something interesting work. They made use of nanocellulose. Look at this picture. They made nanocellulose aerogels, lightweight aerogel. Manufacturing is very simple. You disperse nanocellulose in water and go for a freeze drying. You can make this sort of foam-like structure. But Finnish group did some interesting chemistry. Look at this. Finnish group did a coating on the surface of this nanocellulose using TiO2. This is a TiO2 coating. 7 nanometer coating they gave. You know why did they do that? To make the surface hydrophobic. Once you do that, look at this picture. You sprinkle this nanocellulose aerogel in seawater. The red is oil. All the oil is absorbed by this aerogel, which is hydrophobic. Oil is hydrophobic. And this aerogel cannot take water because it is hydrophobic. And you collect all the oil and collect all this aerogel. You can squeeze out and reuse the oil, or you can burn the oil. So they have, scaled up this technology for removing oil from water. Let me show you another important slide for water purification. We all know that water has contamination with heavy metals. It could be chromium, it could be copper, it could be nickel, it could be lead. I wanted to show you a very important slide. Chromium-6 removal. Chromium-6 here is electronegative. So if you make the surface of nanocellulose electropositive by introducing amine group, you can see the absorption of equilibrium absorption of chromium. Beautiful absorption of chromium. So you can remove chromium. You can also remove nickel, cadmium, lead. The only thing is you do the required surface chemistry. So we are able to remove all sorts of metallic impurities from water. Nowadays, we are facing the corona issue. So nanocellulose is a good answer for that. Nanocellulose can remove bacteria and viruses. Probably you know that bacteria are bigger in size. And by size exclusion principle, you can remove bacteria. You just filter it, all the bacteria will be retained by the filter at the top because bacteria are quite bigger in size. But if you want to catch viruses, they are very small, nanometer size. They usually try to get away from the filter. If you want to remove viruses, you have to do some chemistry. The chemistry is, again, reacting with the polyvinylamine. You introduce amine group on the surface of nanocellulose. You all know that these viruses have a protein envelope which is negatively charged. So you can have electrostatic interaction between the virus and the nanocellulose surface. And you can remove, you can see the logarithmic LRV values, the logarithmic removal values. They're pretty good. So you can remove viruses, bacteria, etc. Look at this slide, a gentleman suffering from high degree of burns on his face. And his face is covered with nanocellulose aerogel. And this is a wonderful material for tissue regeneration. Let me show you another interesting example, which we have done some nice work with Brazil. My Brazilian counterpart made polyurethane material for hot valve manufacturing. That is PU, polyurethane. But this PU suffers from weak mechanics. So we thought of reinforcing this material by using nanocellulose extracted from pineapple leaf fiber. I wanted to show you very interesting data. Look at the modulus of PU, 37.5 megapascal. And this value goes to 992.4 megapascal if you add 5% of nanocellulose. So you can strengthen medical grade polyurethane, manufactured nanocellulose, polyurethane, prosthetic hot valve. And we had a series of publications. Now let me show you use of nanocellulose for own healing applications. It's an excellent antibiotics. Let me show you a very nice work of Sebastian Moritz from Spain. Sebastian and his group made nanocellulose aerogel. Manufacturing is very simple. You go for a freeze-drying process. And then he introduced antibiotic into this. So this is an excellent platform for sustained release of antibiotic. You look at the release profile of antibiotic from nanocellulose. Let me show you another example from the work of Professor Liu from China. Professor Liu and group, you know what they did? They combined nanocellulose and collagen. They made nanocellulose collagen nanocomposites. They made aerogel. You can see the picture of the aerogel. Extremely porous. The porosity is something like 95%. And water holding capacity is 4,000%. And this is an excellent material for wound dressings. You know, it can absorb all the water. Since it's combined with collagen, the biocompatibility is super. Let me show you another interesting slide. Nanocellulose could be a good material for reinforcing commercial membranes. You see, commercial membranes are usually made of electrospinning technique. And if you look at commercial membrane, look at this membrane. This is made from polyacrylonitrile, the blue one. Look at the modulus, look at the mechanics, poor. But if you give a coating on the surface using nanocellulose, one side coating, you see the strength goes up. Two side coating, still the strength is further increased. So dear friends, the commercial membranes could be reinforced by coating with nanocellulose. Let me show you what we have done during the COVID time. We submitted a very big proposal under the NSF grant, National Science Foundation of the US and DST of India. Several universities in India involved, and the university in the US was Georgia Tech. You know what we proposed is, we proposed a tri-layer mask. You can see the picture of this. 3 layers, the outer layer, the middle layer, which is black, and is the innermost layer, a triple layer mask. And the outer layer is made of polyester fabric coated with a polyelectrolyte. This is a polyelectrolyte coating, anti-adhesive coating. It can repel coronavirus. You see, if corona is coming, virus is coming, the virus could be repelled by this outer layer. However, if you are careless in wearing mask, there are a lot of people, you know, they are very careless in wearing mask. These coronavirus can get into the mask sometimes. So we have a very important middle layer. And this middle layer is made of electrospun nylon engraved with nanocellulose, which is positively charged. And we also put some curcumin in this layer. Curcumin is antiviral. If at all some coronavirus is getting into your mask, this layer can kill this coronavirus because you have positively charged nanocellulose. It can interact with the negatively charged coronavirus, and this protein layer can be deactivated and you can kill the virus. And the innermost layer is made of cotton. And you can see our design: outer layer, the middle layer, and the inner layer. And we also have a plan to make it by 3D printing. So several universities involved in this process. Yeah, we have some problem with the opening. Just a minute. We are also into sensors. We are also into sensors. We are able to manufacture sensors from nanocellulose. Maybe I will show you one slide how we made senses. Can you all see my slide?
Yes, sir.
Yeah,
We can.
friends, can you see my slide?
Yes, sir, we can. Yes, sir, we can. We can, sir.
Can you all see my slide?
Yes, sir, we can. We can see.
Okay. So, this protocol, what we have done is we combine carbon nanotube. We also did some hybrid work. We combine nanocellulose and carbon nanotube together. So look at this. This is nanocellulose, this is CNT. And then we mixed it with natural rubber latex. This is rubber latex. We mix them together. We went for a coagulation process. Then we went for hot pressing. And finally, we got CNT, nanocellulose. So now I'm going to talk about the use of nanocellulose for electronic application, for sensing. So I will show you a few slides in this direction. See, what we have done is we have taken nanocellulose and CNT. CNT is a very important nanomaterial. So we have mixed them together. We have mixed them together. You can see this with the natural rubber latex. Kerala has a lot of your coordinator professor was telling about the rubber trees. We have a lot of rubber trees in Kerala. So we have a lot of rubber latex. So we made some beautiful composite, nano composite with natural rubber. And you see, this is our nano composite. I will go to the next slide. This is a very interesting slide for you. See the nanocellulose that we get from nature. This is a dispersion in water. You see how stable they are. 0 hour, 24 hours. But if you look at the man-made, CNT, 0 hour, you get a good dispersion. If you keep CNT for 24 hours, you know what happened? The whole CNT settles down. But if you mix CNT and nanocellulose together, you see it's pretty stable. This is the advantage of hybridizing two nanostructures together, CNT and nanocellulose together. I will show you a very interesting slide. If you make nanocomposite with the CNT alone, a natural rubber, you get a beautiful percolation. I hope there are some electrical engineers in your group. You get a beautiful percolation. This is a percolation process. And nanocellulose form a network and you have a percolation conductivity. But if you mix nanocellulose and nanotube together, both together, you see the percolation shifted to lower concentration of CNT. This is the beauty of combining nanocellulose and CNT together. The percolation could be shifted to lower concentration, a lot of advantages. So we made lots of senses out of it. I will go to my next slide, where we have made a PhD student of mine made EMI shielders. Every electronic equipment, look at the mobile phone. We have an EMI shield inside the mobile phone, which is metallic. So what we have done, we have made nanocellulose from banana stem. This is our nanocellulose, banana stem. And then we mixed with aniline monomer. Look at this. And we polymerized aniline. This is a polymerization process. And what we made is, we made polyaniline, nanocellulose, nanocomposites. Very flexible paper we have made. And I will show you next slide. This is the totality of the process. My PhD student has taken nanocellulose dispersion made from banana stem, injected aniline, went for polymerization process. We did a vacuum filtration process and hot pressing using a press, compression molding press. You know what we made? We made conductive paper. Very thin conductive paper we have made. Very, very flexible, thin conductive paper. What is the use of this material? You can see the next slide. It's extremely conductive. Look at the conductivity. And this is a wonderful material for electromagnetic shielding. Your mobile phone has metallic shielder, and we have shown that this metallic shielder could be replaced by nanocellulose shielding material. Nanocellulose combined with polyaniline. Let me show you another interesting work. We are also into fish waste. India has a big, very big seashore, and we have excellent fish industry. And these fish industries produce a lot of waste. For example, the shell of the prawn, crab shell, etc., etc. What we are doing is we are able to extract nano chitin from this. And the extraction process is very simple. You take the crab shell or prawn shell, you go for a acid washing, you get nanoscale chitin. This is chitin nano viscose, this is nanofiber. So we are able to make—
It's 11 hours.
We are able to make nano viscose or long nano chitin from fish waste. Let me show you the application of this. Maybe one slide I can show you. Look at this, is the nanochitin extracted from the crab shell. Simple acid washing, like in the case of nanocellulose. And this is highly hydrophilic. You can see hydroxyl groups. But if you do a small chemistry, reacting with the bromohexane hexadecane, if you react this with the bromohexadecane, you know what you get? You can introduce a lot of alkyl groups. These are all alkyl groups. If you do that chemistry, the surface of nanochitin becomes hydrophobic. You see the next slide. This is nanochitin, where the water contact is not very high. It could be around 75. But if you react with alkyl group, you put alkyl group, you can make super hydrophobic surfaces. The contact angle is 158.2. Very high contact angle. So dear friends, by making use of the fish waste, we are able to make super hydrophobic surfaces. And you might ask, what is the use of this hydrophobic nanochitin? Excellent additive for oil. You can control the viscosity of oil by using this. Let me show you the next slide. A PhD student of mine went to Slovenia. We have very strong Slovenian cooperation. And what we have done is, my PhD student made nanochitin from the crab shell. Then he went to Slovenia, and we made some beautiful filters by combining nanochitin with PVDF. And he wanted to remove some dyes in water, textile effluent, indigo caramine dye. This is a very interesting result. If you use the commercial filter PVDF, the percent of removal is only 23%. But if you combine PVDF and nanochitin together, look at the removal efficiency. The dye could be removed up to 88.9%. So this is the beauty of combining combining nanochitin and PVDF. We are also into, dear friends, we are also into waste starch. We are not touching the food sector at all. We collect only the waste starch. It could be potato starch. In Kerala, we have a lot of tapioca, cassava, rice waste, wheat. So these are all very interesting material. We wash them and use it. This is tapioca. In tapioca season in Kerala, we have a lot of tapioca waste. And what we do is, as in the case of manufacture of nanocellulose, we do an acid washing. And we are able to make nanocrystals of starch. See, you can see an electron microscopic picture of nanocrystals from starch, the waste starch. You can make it from potato, you can make it from cassava, tapioca. Thanks to Alan Dufresne, he is a pioneer in this field from Grenoble, #1 worldwide. Dufresne was in our laboratory several times. And I want to show you nice work done by my PhD student, Rajisha. Rajisha took natural rubber, latex, looked at the mechanics. You see, look at the modulus, and natural rubber is a weak material. Modulus is low, especially modulus is low. Of course, it can undergo Saint-Louis crystallization and then the strength is high. But if you put increasing concentration of nanochitin, 5, 10, 15, up to 20, you look at the improvement in mechanical properties. The modulus increases, the strength increases, without much of sacrifice of extension. See, natural rubber extension is up to 1,600. But 20% of nanocrystal, we got up to something like 1,200, pretty good. And you see, my PhD student made a beautiful cartoon. These are all nanocrystals. Nanocrystals of starch formed a network inside the natural rubber matrix. And natural rubber chains are immobilized by this network. As a result of this, the mechanical properties have increased remarkably. I'm going to conclude my lecture. You see, agro waste like wood flour, fiber, coir, pineapple, all sorts of agricultural waste are very interesting. Please don't throw away. Please don't burn them. You can make fantastic nanomaterials. Cellulose nanofibers and nanoviscose. Wonderful material for reinforcement. Plastics, polymer, reinforcement. Wonderful material for water purification. Wonderful material for wound healing. Energy storage. EMI shielding. And please don't throw away the waste of the fish like prawn, the shell of the crab, the shell of the prawn. You can make exciting nano chitin fibers and chitin viscose. A very interesting filler. You can use it for water purification. You can use it for soil purification. You can use it for tissue engineering. You can use it for heavy metal removal. And finally, the starch that you get, the waste starch from tapioca, from potato, the waste, the starch you get from the agricultural field, the very interesting material. You can make nanocrystals and nanofibers of starch. Again, an exciting filler for polymers. So, dear friends, I am posing a question to you. Can we become a zero waste planet? My answer is yes. The only thing is we have to intelligently utilize all these materials, transform them into advanced functional materials. So we all have to create a zero waste planet for the coming generation. And we can make beautiful, sustainable, green nanomaterials from our agricultural waste. I would like to thank Professor Siena Rao, particularly. He has supported me a lot. Hardwood Siena Rao is several times in my university. I have close interaction with him. Nano Mission supported us up to the tune of 30 crores of funding. We have all the high-end machines. I'm thankful to ISRO, CSIR, DBT, AICT, you see all the funding engines in the country supported me. The Royal Academy of Sciences, Atomic Energy supported me. Look at the international funding, India, France, India, Sweden, India, Slovenia, the Royal Academy of Sciences, India, Brazil, DuPont, General Cables, Surface Tool, Czech. All these organizations supported me. Industrial funding from MRF Tires, Apollo Tires, now we have entered into a contract with Apollo Tires. And I have lots of collaborators. Daniel from Brazil, Nandakumar, my colleague, Fernando from Brazil, Alcides from Brazil, Matthew from Sweden, my former coworker is a professor in Sweden now, Guy Brohens from France, Maya Johnson, my coworker, is a professor in South Africa. Didier Ruxel from France. So I have a network of collaborators worldwide. You can see my group in chemistry. In France, this is me. We have a pretty big group in chemistry, nanoscience and nanotechnology. And please visit me in Kerala. We are not very far from Kerala. Please visit us after pandemic. And Kerala is one of the India, and your coordinator already told me that we have beautiful greeneries and backwaters, beautiful backwaters in Kottayam. We have boatways, houseboat, old temples. Kathakali is the traditional art of Kerala, Mohiniyattam. So please visit me after the college. And this is our campus. We are organizing a big meeting, International Conference on Macromolecules, September 10, 11, and 12. In our meeting, all most welcome to attend this meeting. And I'm not going to objects from Xavier. It's not an open access. So Nanoscience is very close to 7.8. So much for your patient hearing, and I'm very pleased to answer questions. Thank you.
Professor Thomas, I really would profusely thank you for being with us. Of course, we will not let you go immediately. There are a few questions in the chat box. Can you access your chat box, Professor Thomas? Can you access your chat box?
I will read my chat box.
Yes, because we have asked our participants to post questions there. Maybe you can switch off your video because again, there is some disturbance in your audio. Yeah, maybe you can look at the chat box. If you can't, I can read out the questions for you.
Yeah. How collect elements without burning waste material?
Oh, if you are looking from there, you have to go back. Okay. So you can scroll. You can scroll up and see from. Okay, maybe you are not able to see the entire thing.
Yeah. I will read whatever questions I can see
remaining
now.
Yeah, remaining I will read it out.
Yeah, let me answer this question. How collect elements without burning waste materials? You see, my dear friends, waste you can burn. Of course, you can get energy. You can have a lot of things. But one thing you should not forget, by burning stuff, you pollute the ecosystem. So burning could be the last strategy. Without burning, you have a lot of other protocols. You see what I've done. Take the agricultural waste, you extract the fibers, and rest of the stuff you can make beautiful, you can go for composting. That is what I do. So burning could be the last resort. Should be controlled burning without affecting the ecosystem. So you can do lots of protocols. Fish waste, don't go for burning. You do an extraction process and you take the nanomaterial. And the next question is, what are the applications of sustainable green materials in automotive sector, hardcore industry? Oh, range of applications. You see, nanocellulose, nanochitin, nanostarch, they're all very exciting material for reinforcement. You can increase the strength of the material. If you look at sustainable material, cellulose, if you look at Benz car, you look at the interior of Benz car. Now I'm discussing with the Benz Bangalore. You see, Benz car is using something like 15 kilograms of natural fibers, or not in the nano scale, in the micro scale. But now we are discussing the Benz to utilize nanocellulose for polypropylene nanocomposites for automotive interior applications. So lots of applications for automotive sector, a lot of applications for sensors, lots of applications for energy storage, lots of applications for biomedical. Explain conductivity process. You see, conductivity, somebody asked a question, conductivity. Look at polymers are generally non-conductive electricity. You have no free electrons. So what we do is we introduce conductive fillers like carbon nanotube or graphene into a polymer. After the threshold concentration, critical concentration, they form a network. And then you have a beautiful conductive network. Electrons can easily pass, or it can also do hopping, and the material gets reasonable good conductivity. There is another question. Dear professor, while extracting nanocellulose, strong acids and other chemicals are used. How to dispose such chemicals? Is cryocrushing is a practical method? This is a very interesting question. See, worldwide, so dear friend, using strong acid is not eco-friendly. Of course, in industry, you have to reuse all acid. But now we are actually going through a mechanochemical process. Cryocrushing, the questioner asked, the gentleman asked a question of cryocrushing. Cryocrushing is a good way. But the only thing is you have to use a lot of liquid nitrogen. You have to cool the fiber and go for crushing. Grinding is a good method. So what we have found is you can use a combination of both chemical and mechanical. There's another question. As soon as the session ends, the participant, oh, sorry. Is there any other method to extract nanocellulose which is eco-friendly? I would say mechanical process, grinding process, which is eco-friendly. And we are working on another technique by bacterial transformation, biological transformation process. It's not yet completely successful. I would say biological transformation is the most eco-friendly technique. Otherwise, mechanochemical. There's one gentleman said, I visited your lab in 2011. I'm glad that you visited my lab. You are welcome again to my laboratory after the pandemic. There's another question. Dear professor, while extracting nanocellulose, okay, cryocrushing is a practical method. Cryocrushing has a disadvantage because you have to really cool this material using liquid nitrogen. So cost performance ratio has to be looked into very carefully. Let me see.
Sir, Professor Thomas, actually, you logged in late. Actually, there were some more questions which were posted on the chat box much earlier to that. I will read out a couple of questions. If you do not mind, please answer, sir. This is a question from Ziauddin Sheikh. What is the best possible route for metal matrix composites production with natural fibers or utilization of waste materials in MMCs?
I'll tell you, this is a very interesting question. Metal matrix, if you go for high temperature mechanical processing, you cannot use it for metal because metal process metal filled material because the thermal stability of this material is in the range of 300 degrees Celsius. So you cannot use for metal matrix composite materials where you have to utilize a high temperature for processing. That's an issue. Some of the metals which could be dissolved in a solvent, then you can go for. That is basically for making films and fundamental studies. If you can dissolve in a solvent, pretty okay. You can dissolve the cellulose in this solvent, and you can do a solvent processing technique. But mechanical mixing process using metal processing is very high temperature. This material cannot survive because the thermal stability is not as good as metals. Metals are very high thermal stability. Yes, more questions, please.
Yes, there is another question. What is the best possible route for MMC composite production with natural fibers or utilization of waste materials in MMC? That's over. Sir, can you suggest a green composite that has higher heat transfer rate compared to conventional materials of heat sinks?
Yeah, you see, higher heat transfer rate, what we have recently suggested is you can make use of hybrid structure. Hybridizing, graphene with nanocellulose. We have made some nice combination. So hybrid structure should be very good. Graphene with nanocellulose is a good material for good heat transfer.
Dr.
Graphene could be a
Ishrat,
good candidate.
Dr. Ishrat wants to know if do you provide research support to private college faculty uh, in the facilities that are available in material science area in your university?
Of course, you see, our facilities like high-resolution electron microscope, NMR, then atomic force microscope, scanning electron microscope, all the facilities are open. They're all purchased under the central funding from the government of India. One of the requirements in government of India is just be open to all. Please write to me. I can direct your request to the corresponding head of the department, and you can get it done. Everything functional. Most of the machines are functional, and they also charge very nominal charges. You can get it done. No issue. And we have lots of users for every machine.
Yeah,
If you
Professor
want to
Thomas.
stay sometime,
Go ahead.
you are most welcome. We'll arrange everything for you.
That's very, very nice of you, sir. Professor Thomas, dear participants, if anyone wants to ask a question orally, please unmute yourself and you can ask a question orally. Maybe we can have another 5 minutes or so.
Definitely, no issue in that.
Yeah. Anyone wants to ask a question?
Professor,
Yes.
yeah, just now you talked about 3-layer mask, sir.
Yeah.
We normally now we use N95 mask.
Yes.
So how it differs from that, sir? Can you just throw some light?
Look at all this masks. 95 means the filtration efficiency is 95. And European Union has efficiency mask. So our mask, in agreement with our, the standard mask, we can be able to make N95, N98, N99. We can have no issue in that. We are able to satisfy all the standard protocol. But our mask is quite
What do you want?
efficient.
Tell me first.
A very interesting layer, which is
Is it available in the market, sir?
no, not yet. We are patenting it, not yet. Which are the outer layer is coated with an anti-adhesive layer, polyelectrolyte layer. It can repel coronavirus.
Okay.
Before mask, they're all coronavirus will rest. So that is why when you wear mask, please don't touch on the mask.
Okay.
If you touch on the mask, it will be contaminated. The mask is different.
Yes, sir.
Coronavirus will not be a mask. It will be repelled. And if at all some coronavirus getting into the mask, that will be killed by the layer. That is the beauty of this mask. But
Thank
not
you,
only
sir.
normal mask. Virus.
Dear participants, if I have missed out any question to be asked from the chat box, if you want to ask yourself, please go ahead. Any other question? Another 1 or 2 questions from participants? Sir, I had a question. I was wondering if any work has been done in processing fibers from 2 different, let's say, vegetative material. One is this water hyacinth, which floats on the backwaters of Kerala, which is a big problem for the boats. And well, do you have you tried to use those fibers from these plants, this water hyacinth? And also the other material I'm looking for is mango shells. Mango seeds or mango shells also has very strong fibers, I'm told. So have there been any work done in your lab or elsewhere which brings in these 2, plants or products?
Yeah, these questions are very important because if you look at the our waterways are greatly affected by the water hyacinth. So I have a very interesting project to extract fibers from water hyacinth. The problem with water hyacinth is the amount of fiber that you get from water hyacinth will be 1%. Very small amount of fiber. The rest of stuff you have to go for composting. So we designed a machine recently, and we are now working with some of the panchayat and villages, panchayat leaders to scale up this process and to make the remaining waste for biogas. So we get beautiful 1% of fiber, and this we are setting up a company, and we also got some funding from an organization in the United Kingdom to mechanize this process and collect all this water hyacinth and then make fibers out of it. And you can make quite nice, nice textile out of it, water hyacinth fibers. Another thing we have done with water hyacinth is we've collected water hyacinth and then we dried them. We made beautiful handicraft. So if you come to Kumaragam, you can see this sort of operations are going on quite nicely. You can make beautiful handicraft. So these projects are going on. This is a very nice idea you suggested, the shell of the mango, the kern. That could be a good material because we produce a lot of mango in this country. And, if you can collect all this waste, that could be powdered and utilized. Yeah, this is quite interesting. Some work has been done with the groundnut shell, and excellent work has been done on cashew nut. Cashew nut shell is a very wonderful material. We can make beautiful polymers out of it. So your question is very relevant, and with the mango, we are ready to do some good work. I'm thinking of in the direction using mango shell. Yes. Very, very nice question.
Yes,
Thank
sir.
you for your comment.
Thank you. If are there any other one last question from any participant, please? One last question.
Yes, Professor. Professor, I'm Mutalakshmi from Kalasalingam University. Nice to see you, Professor. It's a very interesting talk. One question from one doubt, sir. Some of the plant fibers, it is not having good mechanical strength, but it is having lot of opportunity due for more applications. So in that way, how to improve the fiber mechanical character, sir? Any alkali treatment is possible, sir, for improving the property of fiber?
Very nice question. You see, the properties of fibers could be enhanced by different ways. One is you can have a chemical treatment. You said alkali treatment could be a good way. You can use sodium, so you can have permanganate treatment, peroxide treatment. We have developed a series of treatments, saline treatment. So by giving proper treatment, you can improve the properties of natural fibers. Second way of improving the properties of natural fibers is by hybridization. You hybridize with another fiber. So if you look at our work, we hybridize weak fiber with a strong fiber. Look at coir fiber. Coir fiber has got a very high lignin content. The mechanical strength of coir fiber is not that good. But if you look at pineapple leaf fiber, it's very strong. So you can combine these two fibers together and make a value-added material. So hybridization and chemical treatment are the two ways you can improve the strength of fibers. Good question.
Thank you, Professor.
I think Dhananjay was wanting to ask a question very briefly, quickly.
Yes, sir. One question that when you discuss about activated carbon and cellulose, both are from agro product. So you are giving emphasis in nano cellulose. Why not agro product is activated carbon is good compared to nano cellulose?
This is again a very interesting question. See, we have made carbon from a variety of agricultural materials. Activated carbon could be made from shell of many trees, especially shell of many trees. We have made activated carbon as well as a good carbon for battery electrodes. You can see one of our ACS publications. We made a beautiful carbon from these bio waste by controlled pyrolysis. We can make beautiful carbon, and carbon has lots of utility, for a variety of applications. Even it's a good material for water purification. So activated carbon, very interesting material. We are also making activated carbon from coconut shell. It's a very interesting material for water purification. Thank you for your very interesting question.
So I
Thank you,
think I'm afraid that we may have to come to the end of this program.
You
Uh,
know,
so,
I have a project on making graphene from bio waste. Controlled, pyrolysis. You can also make graphene from all these biological sources, bio waste. Yeah. Thank you.
yes, sir. Sir, I'm afraid we may have to stop, unfortunately. We would love to have listened to you as much as time permitted. But, well, actually, it's good that we started early. So that, I mean, I'm very, very thankful to you for having extended your time and rescheduled your engagements and sharing with all our viewers and our participants such wonderful, enlightening thing. We have, for many of the problems, we have solutions in our own backyard. We just have to look at them. And we are thankful to you for opening our eyes to such solutions. And Kerala is a wonderful state. It's my favorite state. Kottayam and Kumarakom is beautiful. Kottayam with all the Valyapalli, Cheriyapalli Orthodox churches, it's beautiful. And I have read that Kottayam is a city of, it's a place of 3L, they say. L, latex, lagoons, and literature. I mean, they are known for literary giants. And of course, now we also have a technology giant from there, from that as well.
Thank you.
Yourself, sir. Thank you very much once again. A big, big thanks from all of us, from the ISCT, ATEL, from MSRT, and the participants. Thank you very much, sir. Thank you for being with us. Thank you, sir. Thank you, sir.